All right, Calc. So as I said, I was going to leave this video for you guys to do this last example and then a little bit at the bottom. So this next example we have is a particle moves along the axis such that its velocity can be modeled by the function v of t equals t times 1 plus 1 over t squared for t is greater than 0. Find the position of the particle at t equals 3, given that x1 equals 4, so x is the position function here. When I took calculus, the velocity, acceleration, position, all that stuff did not make sense to me because I took a vacation to Disney, I think. And I was gone the entire unit, and then I came back, and then it was the day of the test when I came back, so my teacher just gave it to me. I think that was the only test that I failed in calc. But didn't make sense to me until I got to college. So just a little side note there. But if we're finding a position, what we want to do here is integrate. So I'm going to integrate this. Or I'm integrating this, really. This is v of t. So there's a couple ways we could do this. And I think the way that a lot of you guys would do is to take the indefinite integral. Indefinite with an E. And you'd take the indefinite integral, why is the bell going off? Indefinite integral of that t plus 1 over t, or times 1 plus 1 over t squared dt, and just evaluate the position function of that plus c, and use this information here to find c, and that's perfectly valid. That would work just fine. But the issue with that is, what if they give you a function that you can't take the indefinite integral of? What if they give you a function, it's a non-calculator active part, they give you something that you can't integrate? So in that case, wait, did I say it's a non-calculator active part? It would probably be a calculator active part in that case. My bad. Yeah, if it's something you can't integrate, it would be a calculator active part, but your calculator can't do indefinite integrals. Your calculator can only do definite integrals. So we are going to do the definite integral here. And what we're going to do, instead of the indefinite integral, is the net change. So I know that the net change here, the position of that particle at time t, is going to be modeled by, well, at the beginning, at x of 1, it is at 4, and then I want to go from 1 to 3. So it's going to be the integral from 1 to t, in this case it's going to be 3, of x, instead of t, times 1 plus 1 over x squared dx. And if I plug in that t, I get everything changed to t, which is our velocity function. But this integral from 1 to t, that represents the net change in position from 1 to t. So what I'm going to do with this x times 1 plus 1 over x squared, I'm just going to multiply this out. So that's going to be my best thing to do here. And I've seen a lot of you guys doing the box method on your assignments, so I may as well do it as well. So 1 times 1 is 1. 1 times 1 over x is 1 over x. 1 times 1 over x is 1 over x, and 1 over x times 1 over x is 1 over x squared. Combine all my like terms, we're going to have 1 plus 2 over x plus 1 over x squared. And then I'm multiplying everything times x. So that's going to give me x plus 2 plus x over x squared is the same as 1 over x. So this is the function that I'm going to be integrating here. And I'm going to be doing the position at time t equals 3, so x of 3, is going to be 4 plus the integral from 1 to 3, because again, t equals 3, of this x plus 2 plus 1 over x dx. Let me integrate this. So I'm going to have 4 plus the integral of x is just 1/2 x squared. The integral of 2 is 2x. The integral of 1 over x, well, that's x to the negative 1. Or, wait, no, it's just going to be ln of x. What am I saying? The natural log of the absolute value of x. And I'm evaluating this from 1 to 3. So I'm just going to plug in 3, plug in 1, subtract them. So I'm going to have 4 plus, let's see, if I plug in 3, I'm going to have 9/2. I'll put this all in parentheses. 9/2, and then 2 times 3 is plus 6, plus the natural log of 3. Yeah. Then minus, and I'll do parentheses, plug in 1. So 1 squared is 1 times 1/2 is 1/2. Plus 2 times 1 is 2. Plus the natural log of 1. Well, the natural log of 1 is 0. So I'll just say plus 0, even though I don't need to. So let's see. This is going to work out to 4 plus, I have 9/2 plus 6. Well, 9/2 minus 1/2 is 4. So it's basically like 4 plus 6, and then minus this 2 over here. So 4 plus 6 is 10, minus 2 is 8. And then I also have plus that natural log of 3. And then 4 plus 8 is 12 plus the natural log of 3. And this tells me the position of that particle at time t equals 3. 12 plus the natural log of 3. So we want to know our net change function. We can just start with what we're given, start from the original time, and then just add, x of 1 onto that. So x of 1 was 4, so we added the 4 onto that, which is our net change function. All right, now let's look at just a summary of the stuff that we did today and some other integration techniques that you may want to use. So with a problem like this, if I was integrating this, what I would probably do here is I would multiply these out. I would have 1 plus e to the x times 1 plus e to the x. So 1 plus e to the x times 1 plus e to the x. When I multiply that out, I'm going to have 1 plus 2e to the x plus e to the 2x. So my method was multiply / expand. So there's a method we can use. And there are going to be more methods that I'm not listing here, but there are some. with a problem like this one, the numerator and denominator don't have the same degree, so I'm not going to be dividing, but I see the numerator is just two terms being added together, so I'm just going to split them up. So I would turn this into 1 over x squared plus 1, which we can see now that is the, what is that, the tangent function? Yeah, or the arctangent, I mean, plus x over x squared plus 1. And with that one, we would be able to use substitution to integrate it. So with something like this, we would just be able to split it up into two separate terms because we can split up the numerator. So my method here is separate the numerator. Now this third one, this one is a bit devious. And I would certainly not have thought of this. It took me a while to get this one. But what we want to do with this one is actually complete the square. So, you know, this, I'm just going to rewrite this as 3 over, let's see, x squared plus 2x plus blank, because there's something else we're going to be throwing in there, plus that 5. So remember, to complete the square, we have to take half of b and square it. So b here is that 2. So half of 2 is 1. 1 squared is 1. So this is going to turn into 3 over x plus 1 squared. X plus half of b squared. And then I have that plus 5. And as I said, I took half of b and squared it and added it in. So I have plus 1. But I can't just pull that 1 out of nowhere. I have to basically subtract 1. So I'm adding 0, basically. If I add 1 and subtract 1, it's like adding 0. But this part here turns into this x plus 1 squared. So now outside, I have 5 minus 1. So I wouldn't have 5 there, actually. I would have 4, because it's 5 minus 1. And now I have 3 over x plus 1 squared plus 4. And we can see that this is actually going to be the arctangent, because I can do the square root of x plus 1 squared. I can do the square root of 4. Use the arctangent property there. So our method for this one is complete the square. I don't think there are going to be any of those on your assignment for tonight, but good luck, Charlie. For number D, this one, we do have two, or the numerator and the denominator both have the same degree. They're both x squared. So this one I am going to be using long division. When they don't have the same degree, we need to come up with a different method, or if the degree of the denominator is less, at least. If the degree of the denominator is greater, the degree of the numerator is greater, then we're able to use our long division. Or if it's the same, you know. So let's see, I have that x squared plus 0x plus 1, and I'm dividing that into x squared plus 0x plus 0. To get that x squared into this x squared, just multiply by 1. Goes into that one time. So I got x squared plus 0x plus 1. I want to subtract all that. So I got 0 x squared plus 0x, and then 0 minus 1 is minus 1. So I have minus 1 over, and that minus 1 is my remainder, over the divisor, so x plus 1, or x squared plus 1. And again, that 1 over x squared plus 1, that's an arctangent. So our method here was long division. And finally, this fifth method here, or this fifth example here, we have the cotangent squared of x. So if I were to integrate this, there is no rule for integrating cotangent squared. But I know my trig identities, and I know that there's a trig identity that says 1 plus the cotangent squared of x equals the cosecant squared of x. And I can subtract 1 from both sides. So I have the cotangent squared of x equals cosecant squared of x minus 1. And even though there is no rule for integrating the cotangent squared, there is a rule for integrating the cosecant squared. So now that we have the cosecant, we can do it. So I have this cosecant squared minus 1, and that's much easier. So know your trig identities, especially those Pythagorean identities. So as I said, that's really it for today's notes. I did want to get to that in class, but we didn't get to it. That's it for today. And I will see you guys tomorrow. Have a great day.